Okay, now I can start sharing again. So we're looking at day 24 notes. We're looking at this example 3, and we're trying to figure out what elements of A are going to be in an ordered pair together. They're in an ordered pair together. A, B is in the relation if A mod 4 is this equal to B mod 4. That means if when we divide A by 4, we get the same remainder because A mod 4 is the remainder that
Mhm.
A yields when it's divided by 4 as the remainder that we get when we divide B by 4. So each
Oh,
element,
okay.
does that make sense?
Yeah, okay. I'm trying to see like what we're doing here.
So each element, like 1 is in there, and 5 is in there, but 2 is going to be in there, and 6 and 3 and 4 because every one of these elements of A is related to itself because A mod 4 equals A mod 4. So all the elements that look like little a, comma little a are going to be in there. But
Okay.
that's not all. Let's think about 1. When we divide 1 by 4, like 1 mod 4 is 1, right? It's 4 times 0 plus 1. But there are other elements in A that yield a remainder of 1 when we divide them by 4. For example, 5. When we divide 5 by 4, we get a remainder of 1, right? Because 5
Yeah.
is 4 times 1 plus, so the quotient is 1. But we really care about the remainder. It's 1. What other elements in A yield a remainder of 1 when they're divided by 4?
5, 9. Let's see here.
And that's it.
Yeah, that's it. Yeah.
Yeah, it's 1, 5, and 9. See how they're kind of separated by a jump of size 4 from each other?
Yeah, I see that.
So 1 is related to 5 is related to 1, 5 is related to itself. 1 is related to 9, and 9 is related to 1 because they, yield a remainder of 1. Their mod 4 is the same. But 9 and 5 are related, 5 and 9 are related, and 9 is related to itself. So all these first 2 lines of ordered pairs come from the fact that they are all given the same remainder, namely 1, when they're divided by 4.
Mhm.
Then we move on to 2. What's the remainder we get when we divide 2 by 4?
2.
It's 2, right? It is its own remainder. So 2 is related to itself because 2 gives the same remainder mod 4 that 2 gives. But 6 also yields a remainder of 2 when we divide it by 4, right? And in
Yeah.
fact, right, it yields a
Yeah.
remainder of, did I say 2? It yields a remainder of 2 when it's divided by 4. What other numbers in A give a remainder of 2 when they're divided by 4?
We have
2,
10.
6, and 10. Yeah. See how the jumps are jumps of size 4?
Yeah.
So 2, 6, and 10 are all related to each other. So we have to add all the possible order pairs that show that relation. 2 is related to 2, 2 is to 6, 6 to 2, 6 to 6, 2 to 10, 10 to 2, 10 to 6, 6 to 10, and 10 to 10. See what I mean?
Yeah, I see that.
Then we move on to 3. What's the remainder that 3 yields when we divide it by 4?
3. Oh, by 4, that'll be 3.
Yeah. What other numbers in A give a remainder of 3 when they're divided by 4?
7.
Yep. So 3 and 7, and that's it, because the next one would have to be 11, because, see what I'm saying? But we
Yeah.
don't have 11. So 3 and 7 are related to each other. So we add 3, and 3 is related to itself, right? Because it yields the same remainder as itself.
Yes.
3 and 7, 7, 3, 7, 7. And then the last ones are because 4 and 8 all both yield a remainder of 0.
Yeah,
So
that makes sense.
does
Yeah.
that make sense now?
Yes.
So listen, we can up the ante. We can play this game not on just an A that's finite with just 10 integers in it. We can play this game, this mod 4 game, on all of Z, where we're thinking about all the integers. And it's the same rule. A is related to B, or if you want to think about it as ordered pairs, A, B is in R if A mod 4 equals B mod 4. But here's the equivalent. way of saying it. 4 divides A minus B. Now let's think about what A minus B really is. A minus B is the distance between A and B on the number line. That
Mm-hmm.
has to be a multiple of 4. See, if you look up here, 1 and 5 and 9, they were all related because you can get from 1 to 5 to 9 by jumps of size 4. 4 divides the difference between 1 and 5. That difference is 4. 4 divides the difference between 1 and 9 because that distance is 8. 4 divides the distance between 5 and 9 because that distance is 4. 4 divides the distance between 5 and itself because that distance is 0, and 4 divides 0.
Mm-hmm.
So there's a partition that curly R, this relation, induces on Z, and we can find it by finding the subsets of Z produced by grouping integers together if they're related to one another. Well, they're related if they have the same remainder. So the 4 equivalence classes are 4Z, 4Z plus 1, 4Z plus 2, or 4Z plus 3. Remember when we did this back when we played quotient remainder theorem games?
Yeah, I remember that.
Well, the partition that this particular relation induces on Z is called congruence mod 4, and it splits Z up into 4 subsets. And the subsets basically group integers together if they give the same remainder when they're divided by 4.
Okay. Yeah, that makes sense.
And then we played that game again today. Were you in class today?
I remember. Yeah, we did all that in class today.
Yeah, so we did the same game in class today. But the game that we played was, we went ahead now and called this very special relation congruence mod 4. First, we talked about transitive closure, where we, add all the elements we need to make a transitive set. But then we talked about, oh yeah, oh, by the way, page 3 and 4 are mixed up. I'm going to have to rescan them. Then we defined an equivalence relation, and congruence mod 4 is like a classic equivalence relation. For A is congruent mod 4 to B if 4 divides A minus B.
So
And
what are we doing in example 3 down there?
here we are milking the 2 facts that were discussed in the goals. If we have an equivalence relation, 2 things happen. Every equivalence relation induces a partition on the underlying set. And but the converse of that is if we have a partition of the underlying set, there is an equivalence relation associated with that partition, where we group A and B together in the same subset if they're related by the relation. Okay. So let's go. So what we did was, here's fact 1. Given an equivalence relation R on set A, remember it's going to be reflexive, symmetric, and transitive. There is a partition of set A that R induces on set A. This equivalence relation induces a partition. In fact, the partitioning sets are constructed by putting elements of A that are related to one another in the same partitioning set. You could call it the set A sub I. Remember partitions, we had A1 and A2 and A3, and when we union them up, we get all of A.
Mm-hmm.
So fact 1 says you take an equivalence relation, and from that you can build or go to a partition. So here's where we play the game. I give this equivalence relation on this set A. A's got 1, 2, 3, 4, 5, 6, and a 7 in it, okay? It's got those 7 elements. Here's the relation. Notice it's an equivalence relation. 1 is related to itself, 2 is related to itself, 3 3's in there, 4 4's in there, 5 5, 6 6, 7 7. It is an equivalence relation. It's also symmetric. 1 2 is in there, but so is the twin, 2 1. 4 5 is in there, but so is its symmetric twin, 5 4. 4 6 is in there, but so is 6 4, right? 5 6 is in there, but so is 6 5. So that's what this page was supposed to be, that page. We checked reflexivity. A comma A is in there for every A. The 1 1, 2 2, 3 3, 4 4, 5 5, 6 6, 7 7 were all in the relation. The symmetry, these pairs were all paired up in there. And then the transitivity was a do later. It is a transitive set. You can trust me that this is a transitive set. So part two of this game was given this set. Let's finish the game. We're going to build the partition. Okay, so here we are building the partition. Well, we
Well,
have,
I have a quick question before you move on.
yeah.
Um, for that relation and for the symmetry part, I saw let's say that you want to do 3, 2, and 2, 3. Is that possible to do? To
Well,
put
let's
in?
take a look at the relation that we were given. Do you see 3, 2 or 2, 3 in there?
No, I don't.
So we don't have to worry about it because 2, 3
Okay.
is not in there. Now, if 2, 3 was in here, 3, 2 would sure have to be in there as well.
Hmm.
But it turns out 2 and 3 aren't related to each other.
Hmm. Oh yeah,
Two
because
and
this is
two
that
and
you're
one
saying.
are related to each other,
Yeah.
but three is not related to anything but itself. See, because three is not involved in an ordered pair with anything but itself. So it's going to sit alone in one of these partitioning subsets that we build.
So
But
will this
four,
kind of problem be on the test?
yeah,
And then you're gonna give us the relation, like you're gonna give us like what order pairs are gonna be in the relation.
I might, or we might play the game the other way. We played this game two ways. Let's finish the game this way, and then we'll play it in the other direction.
Okay.
So here I gave you the ordered pairs, and then I asked you to find the partition. And we introduced some new notation for the equivalence class of an element of A. What is the equivalence class of A? It's called square bracket A. It's all the X's, all the elements in A that are related to little a. So here we go. We start with 1. 1 is one of the elements of A. See, 1 is in there. And we ask, what elements is 1 related to? We'll look at the ordered pairs. 1 is related to 2, and of course 2 has to be related to 1. 2 is related to 2 as well. But the point is 1 and 2 are related to each other because they're in ordered pairs together. So when we build the equivalence class of 1, it's got 1 and 2 in it.
Hmm.
But that is actually also the equivalence class of 2 because the equivalence class of 1 and 2 is the same set because they're in there together.
Yeah.
Now 3 sits by itself in a little partitioning set because when you look at this relation, 3 is not related to anything but itself. So
Hmm.
it's all by itself in one of these partitioning sets. But 4 and 5 and 6 all have the same equivalence class because they're all related to each other. Let's take a look. 4 is related to 4, 4 is related to 5, 4 is related to 6, 5 is related to 4, 5, 5's in there, 5, 6, and of course 6, 4, 6, 5, and 6, 6. Those ordered pairs being in this relation tell us 4, 5, and 6 are all related to each other in every way possible.
So what if one of those wasn't in there? Let's say 6, 6 wasn't in the relation.
Then it wouldn't be an equivalence relation because it wouldn't even be reflexive. I wouldn't be able to do that to you. If I
Hmm.
give you one of these equivalence relations, I've got to be sure to include all the pairs to make it work out to really be an equivalence relation.
Okay.
So 6 and 5 and 4 are all together in one of these subsets. And you could name this subset the equivalence class of 4, or you could call it the equivalence class of 5, or you could call it the equivalence class of 6. They're all the same set. And 7's like 3. When you look at this equivalence relation, 7's only related to itself. It's not in any ordered pairs with any other element. So it sits by itself in an equivalence relation. So that's our partition. It's got the set with 1 and 2 in it. That's like our A1. And A2 would be the set that just has 3. The next partitioning set is the set with 4, 5, and 6 in it. And then the set with 7 in it. Remember when we had that exercise, that homework exercise where I gave you collections of subsets and I asked if they were partitions of the underlying set?
Was that one of the due laters for the first class?
It was
Like,
actually a special homework problem.
okay.
All right. Or it might have been worksheets. No, it was special homework. Wasn't it special homework? It's definitely special homework.
Oh yes, 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 yes. The collection. Okay, I know what you're
Right,
talking
the
about.
collections.
I
Well,
know what
those
you're talking
collections either were partitions or they weren't. Like some of them were missing an element,
about.
some of them had an overlap. You're not supposed to have that. Every element in the underlying set, which is A had 1, 2, 3, 4, 5, 6, and 7 in it. Has to be in exactly one of these subsets. And sure enough, every element of A appears in exactly one of these subsets. There's no overlap, but the union of these subsets, A1, union A2, union A3, union A4, is sure enough all of A. This is definitely a partition.
Okay, now that makes sense now.
Oh, great. So we could play the game the other way.
Hmm.
If we have a partition, then there is an equivalence relation. We build the equivalence relation by this rule. If A and B are in the same partitioning set, like call it A sub I, then we put together all of the possible ordered pairs that show that those elements A and B are related to each other and related to themselves. Like little AB has to be in there, but then BA's got to be in there. But AA has to be in there, and so does BB, right?
Hmm.
You got to have all four of those ordered pairs in there. So this is the game where we start with the partition and we build the equivalence relation. So here we go. In example 4, I kind of made A a little smaller. It's just got 5 elements. Here's a partition on A. The first set has got 1 and 4 in it, so they're related to each other. The second set's got 2 and 3 and 5 in it. They're all related to each other. So to find the equivalence relation, it's going to be a subset of A cross A. That means it's ordered pairs where first and second coordinates come from A that is associated with P. So what do? Well, look at the first partitioning set. It's got 1 and 4 in it. So 1 is related to 1, 1 is related to 4, 4 is related to 1, and 4 is related to 4. You need all 4 of those ordered pairs to talk
I
about.
see.
See
Okay.
it?
Yeah.
And then 2 and 3 and 5 are all related to each other. So we need all those ordered pairs. 2, 2, 2, 3, 2, 5. 3, 2, 3, 3, 3, 5. 5, 2, 5, 3, 5, 5. All the different ways that we can pair up the 2, the 3, and the 5, making all these other ordered pairs. And that's it. That's this is an equivalence relation. You can check it. It's reflexive. We've got 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5. So we got all of the reflexive pairs. It's symmetric. 1, 4 is in there, but so is 4, 1. Hey, 2, 3 is in there. So is 3, 2. 2, 5 is in there, but so is 5, 2, right? And 3, 5, and 5, 3. So it's,
Okay.
and it is transitive. That's the hardest thing to check, but it is transitive.
Mhm.
So I gave you a do later where you can play the game both ways. In example 5, I gave you the ordered pairs, find the partition. In example 6, I gave you the partition. I was a little bit mean here. 1 is by itself. That's easy. There's only one ordered pair, right? What's the ordered pair that we get from 1 being by itself? Only,
This would be just 1-1.
yeah. And 2 is by itself, so that's easy.
Give it 2-2.
But now I put 4 elements together. So you're gonna have a lot of ordered pairs to
Yeah.
make sure you get all those. But I'm sure you can. And now we go back to congruence mod 4. You see the definition that A mod 4 equals B mod 4 is equivalent to saying that you can get between A and B using jumps of size 4. See, that's what it means to say 4 divides A minus B. See, A minus B is the distance between A and B. That distance is a multiple of 4. So you can get to from A to B by jumping by jumps of size 4. That's what this means.
And then now I see what you're doing at the bottom here is that like all of them are jumps of 4, but also like you just find one number that has a remainder of. I'm not confused here.
Trying to get this out of my way. I don't know how to get this to go out of my way. See, like for A to be congruent to 7, we got to find something that's a jump of size 4 or a multiple of a jump of size 4 from 7. Like 3 is 4 away from 7. They
Mhm.
yield the same remainder. When you divide these by 4, what's the remainder that you get?
3.
Yeah, and same with 11, because it's 4 times 2 plus 3. So any of these would be solutions for 1. See what I mean?
Mhm.
And then I asked you to jump down to some negative ones. Well, if you jump from 7, you get to 3. But then if you jump again by 4, going to the left, that's when you start hitting -1. then you hit -5, right? These
But
are all
for the second one, the way that you frame the question, because you say find a negative integer a such that a mod 4 equals 7. That's how you say it, right?
uh-huh. A is congruent mod 4 to 7, or A mod 4 equals 7 mod 4. It's the same thing.
So when you say it like that, like I see what you're doing, but I don't get what it has to do with like how do I phrase this question? Um, I guess
Well,
I'm not understanding the translation between like the
mhm.
A mod 4 and then you getting the like -1, -5, -9.
Because these are all congruent to 7 mod 4. Like, what's the remainder you get when you divide 7 by 4? You
You get
already
three.
told me. You
Yeah.
get 3. But you get 3 when you divide -1 by 4. -1 is 4
Oh yes. Okay, I
times
see.
-1 plus 3 to get you back to the -1. You got to come back with a positive remainder, remember?
Mm-hmm.
See, and the other thing is that all these numbers are jumps of size 4 apart. Like to get between -9 and 11, that's 20. The distance between these is 20, right?
Hmm.
Because 11 plus 9 is 20. Well, 20 is a multiple of 4. 4 divides 20.
Yeah.
You can
Okay.
get between -9 and 11 by jumping by jumps of size 4.
So you can just go back. Like another way you could do it is just like go backwards by 4
Yes. And
from
in fact, I'm going to post the video from tonight's lecture. You know, those videos always show up in YouTube in the
Mhm.
263 lectures. And we drew a number line the way that we did on the board today in class. Well,
Yeah.
it's in the notes. So I'm going to post those notes as well because the notes are a little bit different. And that way
Okay.
you can look at it.
Okay.
But yeah, the video is going to get posted here in just a few minutes. And I'm going to refresh these notes and because pages 3 and 4 are out of order. I'm going to fix that. But I'm also going to post the notes that go with the video lecture because, like I said, we drew a number line. It made it a little bit easier to see what the relationship is between 11 and 7 and 3 and -1, right?
Hmm.
Like we drew them on the number line with jumps of size 4 between them. So a little bit easier, not like we did on the board today in class.
No, that's good. I definitely understand this better now, so I'm glad that we went over this. It makes more sense to me.
Good. Yeah, it's deep stuff, actually. This is real mathematics.
Really.
Yeah, this is the real deal.
So when you were doing your PhD, was it just like you just doing math every single day, just like crunching numbers? Yeah.
Trying to. I took some breaks. There people have famous stories about getting their PhDs and what they do to stay sane. One of the things that I did to stay sane was I painted my house, the outside of my house. I had an old 1865 house with gingerbread trim, and so I took time and took several months off, not working intermittently, but painting my house.
Hmm.
But yeah, it was tough. It was DNA computing where we looked at we asked it's like formal language theory. It was theoretical computer science where we asked, hey, if you put DNA strands together in a test tube with some enzymes that only cut if they see certain little subsequences inside the DNA, then what? And then you shape that up with an enzyme that glues things back together, then what is the set of language, words? The words are sequence, you call a piece of DNA a word. What are the words that you would get when that thing comes to equilibrium? In other words, what's the
Oh,
language, the DNA language that you would get? And there was all kinds of symmetry going on. Transitivity, we did not have, but we had reflexivity. We had some really interesting properties of DNA coming into play when we played that game.
so when you mentioned like you say you hear stories about what different people do to like stay
Yeah, like some people learn to play the banjo, or some people build a violin, or
Mm,
some people distract themselves by getting really good at chess, or you know what I mean? Like when you're working on mathematics, you can't really do it. At least I can't do it 12 hours a day or 8 hours a day. I might
mm,
get a good 2 or 3 hours a day, and then I would have to take a break.
wow.
I might sit there for 7 hours, but most of those hours would have been wasted. I,
Yeah.
I found that out. Because you sit and stare at something for 2 hours, it's still not getting anywhere. It's time to get up and do something.
No, 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 I agree with that. And I mean, I felt that way on on a very, very small scale when it comes to like mathematics.
Oh yeah.
I can understand how that could be, for you, someone who's, got their PhD or people who are getting their PhDs, how they're just crunching numbers all day long. So that's pretty impressive.
It's mostly ideas. We're trying to, it's not numbers as much as symbols. Mathematics is more, I mean, some people do a lot of numerical analysis where they actually crunch numbers. For me, it was more like logic and ideas and proving things about DNA. It was more really more like what we do in this class than crunching numbers. Like we don't really crunch numbers in this class as much as think about concepts. See what
Yeah.
I'm saying? Oh, yeah, we had to do some algebra to do an induction proof. But the concept was, hey, you can prove an infinite number of statements with one argument by using this beautiful thing called mathematical induction.
Hmm.
Proof by cases. Oh, sometimes you need to break things up into cases so that you can prove something about something. So
That's very
I
important.
really consider this a course in logic and mathematical concepts more than an algebra course or analysis, numerical analysis course. But
Yeah.
we've dealt with numbers. We certainly deal with the number line and interval notation, right?
Yeah, we did that for like a little bit during during the beginning semester.
A lot of it is about learning to be careful because
Hmm.
sequences of symbols mean something.
Hmm.
Like this is a sequence of symbols, but you look at that, it's called reading, and you have a concept of what this means. Say something to let Dr. G know you're here.
Hmm.
So you have a concept in your mind that's associated with these sequences of symbols. So mathematics is about having maybe a new idea that nobody's ever thought of before and trying to figure out the ways to use sequences of symbols to construct that idea and make it real so other people can be seeing the same thing you're seeing, maybe for the first time.
Yeah, very nice.
Yeah, I think it's beautiful.
Mm.
Mathematics is a way to communicate ideas.
But thank you, Dr. Good. Thank you so much for helping me out. And I understand these concepts better, so I appreciate it.
So glad you came in.
I'm glad I
Now,
came
I
in.
noticed that you did ask for an extension. I'm going to stop recording.